What questions do you have? Things going all right? On which section? The one that was due yesterday? Sure. I don't remember what did it do? Let's see. See if I can guess which one it was. You said the first one? I need to look all again because come on. Give me a mouse. Where's my mouse? Oh, for heaven's sake. Oh, I don't know why I logged in there. Come on. Figure out I have a keyboard. Oops. That one? Okay, so all it's asking you to do, except it didn't give me a C. Where's the C value? Oh, we're okay. Good. Okay, that's what it wants you to do. So what common factor you see in every single term? 3, yeah. So if you pull a 3 out of the matrix, you would have negative 1, 2, 3, 2, 3, 4, 3, 4, 5. Right? If I want the determinant of this, then I can, when I take the determinant, when I pull the 3 out of the determinant, what do you have to do to it? Yeah, raise it to the 3rd power because we have a 3 by 3, right? So the determinant of this matrix will be 3 cubed times whatever the determinant of this matrix is. And then it just wants you to compute what that determinant is. Yeah, that's all it wants you to do. It just wants you to play with that property of pulling the constant out and having to raise it to that power. That was it. Apparently it's 54 for that particular matrix. Did you hear one? Grab yours. Huh? It's today, yeah. Oh. All right. Can I bring it with me? Sure. I appreciate it. Yep. Other questions? Yeah.
Can I get a road book 4B? Question 4B.
The one that I had to change the value, the one I got sent the email about yesterday. Did you get my email yesterday? Yeah. 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 I had to change the problem because I don't know why I was thinking I typed it up because it was not right. Okay. That one I'm not going to grade. I mean, I won't grade it for what you have, but I won't count it. Since I didn't change it till yesterday. Did you say it's been a long time on it?
I spent so long on that problem yesterday. So do I.
That part B?
Yeah.
Oh, yeah. It would help if I would have had the problem right the first time. Yeah.
I know, and then I changed it after you sent the email.
Yeah. Sorry about that.
I figured it out.
You can thank Carly, though. She's the one that found it. All right. Other questions at all? All right. Well, let's continue our discussion with vector spaces. We started doing vectors in Rn, so we'll play a little bit more with that and switch over to abstract vector spaces. Right at the end of class last time, we wrote down 10 properties that vectors in Rn hold, and those are going to turn into our vector space axioms when we start talking about abstract vector spaces. But let's prove some other theorems that are going to be true for any vector space that you would expect to happen, regardless of whether they're vectors in Rn or not. So, even though the book states this particular theorem for Rn, I'm going to state it for an abstract vector space, even though we haven't defined what we mean by that yet. So, let's let V be a vector space. And let C be a scalar. And again, we're going to do real vector spaces. When we say real vector spaces, our constants are, the scalars are real. There are also complex vector spaces and other types of vector spaces that we're not going to worry about. All right, when I say vector space, that comes inherent with a lot of structure, okay? So you have objects in a set that you're going to refer to as vectors. They may be vectors from Rn. They could be functions. They could be matrices. There's lots of different types of objects that you could use as vectors. The important part when we say we have a vector space, you have two operations automatically defined. One is addition. There must be some way to be able to combine two vectors together. And then also the other one's a scalar multiplication. So there's somehow I can change how big of a vector is in some sense. It also satisfies all those properties we talked about last time. Those operations satisfy all 10 of those operations, those properties I mean. So there's a lot of structure inherent in having a vector space. Okay. So you get all of those things for free, and we're going to use those operations and we're going to use the operations and the structures to help prove the following theorem. So the first one says that the zero vector of the vector space, which we again usually denote with a 0, even though it's not necessarily the number 0, doesn't have to be something with all zeros. Okay, it just says that it's the 0 with respect to addition. So that means it's the thing that when you add to any vector, it doesn't change the vector at all for any vector that you use. The theorem is that there's only one. The proof here is pretty short. What's our typical way for proving something is unique in math? Yeah, assume you have two and show that they're the same, right? Okay, that's typically the way we show that something is unique in mathematics. Assume you have two of them and show that they're equal. Okay. So let's suppose that 0 and I'll call it 0 prime are 0 vectors of V. So I have two, show that they're equal. Remember, in order to be a 0 vector, that means when I add it to any vector in the vector space, I get that vector back again, right? If I take any V in the vector space and add the 0 vector to it, I get V back again, right? Right? So in particular, if you take 0 and add it to 0 prime, assuming this is a 0 vector, what do I get back? If I take 0 and add it to 0 prime, what am I going to get back, assuming that I'm using this as a 0 vector? The 0 prime. If I assume 0 prime is a 0 vector, and I add it to the 0 vector, what do I get? 0. Yeah, so that's the proof here. So oops, should be an equal sign. This first statement is that 0 prime is behaving like the 0 vector, right? If I take 0 prime and add it to this thing I'm calling 0, I should get this thing that I'm calling 0 back again, right? If 0 prime is supposed to be the 0 vector, right? Now flip it. If 0 is the 0 vector, and I add it to 0 prime, what should I get back out? 0 prime, yeah. There you go. That's the proof. The end. We assume we had 2 and they were equal. The end. Okay. Notice that when we stated the property, and this is how we'll state the vector, we'll rewrite the vector space axioms here in a little bit. When we stated the fact that there existed a 0 vector, we said there exists a 0 vector, right? We didn't say there exists a unique 0 vector. We just said there's one. It's a pretty common practice in mathematics to never assume something that you can prove, right? I don't need to assume the 0 vector is unique. I can say that if once I have a 0 vector, then it is unique. And I can prove it very quickly in this case. Probably one of the shortest proofs you'll have, all right? Okay. Likewise, the additive inverse of a vector, oops, forgot the word inverse. The additive inverse of a vector in the vector space is also unique. Again, when we stated the property for additive inverses, we just said that for each vector there exists an inverse, but we didn't say there was a unique one. Again, it's because we can prove it. And just like what we did for the previous example, the previous property, previous theorem, we can prove this the same way, right? Assume we have 2, show that they're equal, okay? So let's suppose that W and X are additive inverses of the vector V. Let's say we have 2 additive inverses. Again, what does it mean to be an additive inverse? If I start with V, what does it mean to have an additive inverse of V? What do we do? What does the inverse try to get back to with respect to addition? So we're trying to, what are we trying to do with the V and its additive inverse? What are we trying to get back to? What vector do we end up with if we add a vector and its inverse? Which is in this case the 0 vector, right? Yeah, it's the additive identity, right? That's the whole point of additive inverse, is that I get back to 0, correct? So what can I say about V plus W? If W is an additive inverse, what can I say about V plus W? It's 0, good. What can I say about V plus X? It's also 0. That's what it means to be an additive inverse, right? We add it to V, we get back to 0 in both cases. Both of those things are equal to the 0 vector, so what can I say about V plus W and V plus X? They're equal, right? They're equal to each other. And now I can start working like I would in an algebra problem. I want to get rid of the V. Back in algebra class, what would you do? You wanted to get rid of the V. Yeah, it's subtract it, right? Subtracting is the same thing as adding the inverse, right? So I could either add W to both sides or add Dex to both sides. I get the same answer, right? So let's just add W to both sides for argument's sake. That's just adding the same thing to both sides. What can I do now? I want the v to go away. What can I do now with the parentheses? Because it's wrong word. Associative. There we go. Yeah, it's associative, right? The addition's associative. That's one of the properties we have. And the thing in parentheses is going to be equal on both sides now is equal to what? Zero, right? I wrote v plus w equals 0, but we also know because w plus v is equal to 0 because of commutativity, right? That's where commutative comes in. So both of those are going to be equal to 0 now. And if we add 0, what do we do to the vector? Stays the same, right? So I get w equals x, which is what we wanted to show, isn't it? We're done. That was the end of that group. A little bit longer, but same concept, right? The reason I'm going through these particular ones is because, pardon me, these particular examples is because we want to verify that these are true, but also because it's illustrating the proof technique in math where if you want to show something, there's a 1, you assume you have 2, which shows that they're the same. This is a very, very common proof technique in math. It's okay? Let's see if we can prove a couple of other properties here. And again, these are properties that should look familiar to you and be unsurprising. If I take the scalar 0 and multiply by the vector v, I get the 0 vector. This should be unsurprising, mainly because of things that you've known since grade school, and multiply by 0, you get 0, right? But if you think about it in terms of vectors in Rn, I would distribute that 0 through every component in your vector, and it would just kill every single component, right? You get a bunch of zeros, and that is the 0 vector of Rn. But we don't need it to be a vector in Rn. We can actually prove this using the properties of the vector space. So this is going to be a property of any vector space that we come across, not just vectors in Rn. Doesn't matter what the vectors are. Okay? So the start off here is basically the way you start off other types of problems where you need to do a clever rewriting. You've done clever rewriting of 0 or clever rewriting of 1 for lots of times when you've done things in math, right? You cleverly rewrite 1 and you get a common denominator. Those kinds of things, right? Because if I add 0 and then cleverly rewrite 0, it doesn't change anything. If I multiply by 1 and cleverly rewrite 1, it doesn't change anything, right? So this particular clever rewriting isn't exceptionally clever. It's just because it works. I already have a 0 here, but it didn't matter what that number is. I could always rewrite that as adding 0 to it. That's just a real number, right? I didn't change anything. But now what can I do on the right that I wasn't able to do before? What can I do on the right-hand side? I can distribute, right? I've got a sum and I've got scalar multiplication. That's one of our properties of scalar multiplication, is that it will distribute over that real number sum there. We talked about that for Wednesday. So now the right-hand side is just that. I believe that was property 8 when we wrote it down the other day. It was 7 or 8. Doesn't matter. There's a property number that goes along with it. Okay. What are we trying to get to? What do we want to try to show that 0v is equal to? 0, right? So I probably want to get 0 on one side. What should I do to get 0 on one side? I know there's lots of symbols, but don't get confused by the symbols. Just tell me how to get 0 on one side. Subtract what?
0v.
The 0v, yeah. This is some object, right? It's got symbols in it, but it's just some object. If I want to make it 0, I just need to subtract it or add its inverse, right? Do the additive inverse. We know the additive inverse exists because of property 5. So I'll do negative of the 0 vector, the 0 times v, and then add that. Notice I still have parentheses on the right-hand side because if I add, when I'm adding it to this whole vector, right? So I would have parentheses around that because that's now a single object, whatever that happens to be. But we also know what can we do on the right-hand side now? Yeah, so you're right, I want to straight out the 0v, but I need to regroup it first, right? Yeah. So that's associativity. The left-hand side is 0. This is negative 0v plus 0v. Regroup it. Inside those parentheses now, what do we have? 0, good. And then how can you simplify the right-hand side? No, it is the 0 vector. So if I add the 0, if I add 0 to 0v, what am I left with? 0v, yeah, good. So notice there's a lot of algebraic properties going on to prove this, right? I got a distributive property that I need to know exists here, right? Then I got to know additive inverses exist. I've got to know that I'm able to regroup. This is still additive inverse property, but then I also need to know I have a 0 vector. There's a lot of structure going on to show that 0 times something is 0. Again, this is why math is hard for lots of people, right? There's a lot of math that goes into 0 times something is 0. A lot of math involved in it. Here's what we're seeing right here. You should be able to do the same type of proof. I'm not going to go through it, but another property that you have, pardon me, is that if I take any scalar c and multiply it by the 0 vector, what do you think we should get back out? Yeah, I should get the 0 vector again, right? You would start this proof in the same way that we started the previous proof. I'm not going to go through it. You can go through it for practice. Notice here we rewrote the 0 that we had as 0 plus 0. Right? What do you think how do you think we're going to start that one? Yeah, good. Yeah, we'll do this one as write it as 0 plus 0, or the 0 vector in that case. Right? So you would start with, your first step would be that. Same idea. And then it'd be the same. You should be able to see that it should be the same steps. So I'm not going to spend the time going through it because literally if you can follow the steps for property 3 there, it's the same steps in property 4. Oops. Property 5 says that if we have a scalar times a vector and we get the 0 vector, then from your knowledge of stuff that you've done before this class, what would you expect to happen if you have a product that gives you 0? What would you expect has to happen? One of the two has to be 0, right? And that's exactly what the property is here. Then either the scalar is 0 or the vector is the 0 vector. This is a property that works in vector spaces, but we've already seen that it is not a property that works for matrices, right? We can have two matrices multiply together to give you 0 and neither of them are 0, right? So this is a special property with scalar multiplication in vector spaces, but does not work with matrix multiplication. Also, there are other algebraic structures where it doesn't work. In this case, it says that one or the other has to happen. So again, as a common proof technique in math is to assume one of them is not 0 and show the other one has to be. Okay, so let's suppose, really doesn't matter which one you suppose is not 0. Let's suppose that your C is not 0. We're already assuming that this is 0, right? Now, C is a real number. If C is not 0, what can you do with C that you wouldn't be able to do if it were 0? It's just a real number, so what can you do with C as a real number if it's not 0 that you know you can do, that you know you can't do if it happened to be 0? Divide, right? So let's multiply both sides by 1 over C. We now on the right-hand side have a constant times 0. What did we just prove a little bit ago that a constant times a 0 vector is? 0 vector, right? So I know the right-hand side is the 0 vector. What can we do on the left-hand side? Say that again? Yeah, we're going to cancel the C, but I got to do something first with a property before I can. You got to move the parentheses, right? That was another property. That was property 9, I believe, that we did, correct? Okay. Notice that this is actually a big deal, even though it doesn't look like it's much of a big deal. What kind of objects are getting multiplied here? A scalar and a vector ends up with a... When I take a scalar times a vector, I get a vector. So now I have another scalar times a vector, right? At no time am I multiplying two scalars together here. What am I doing here? I'm multiplying scalars to start with, right? There's actually an algebraic thing going on there, right? That's two different multiplications, okay? So it is a big deal. Even though it looks obvious, it is a big deal. Now I can cancel the C's. I'm left with 1 times V is equal to 0. And what do we know that 1 times V is equal to? V, good. And that was property 10. Okay. One last one that they do in here. They tell you that if I do the additive inverse of the additive inverse of V, what should you get back to? V, yeah. There's not a lot to prove here. Just talk through it. This says I want the additive inverse of this vector, right? That's what that symbol means. We know that additive inverses are unique. What happens when I take V and add it to negative V? What do I get? 0 vector, right? So this is the additive inverse of that. I mean, they're unique, so that is the whole proof. The uniqueness of the additive inverse gives you that. One property that they list in this theorem, one property that also is true that they don't list in this theorem is that if I do the scalar negative 1 times a vector, I really do get the additive inverse of the vector. Again, probably a fairly obvious result, but it's obvious because you've done it so for so many years, you haven't really thought about why it's true. All right, the way this one would work, again, is the same kind of idea. If I want to get at this, I need to be a little bit clever. Let's start with this property again. If I do 0 times v is the 0 vector. Clever rewriting of this 0 that allows me to do a multiplication. Same idea, but I also want to involve this number. What's a clever way to rewrite 0 that involves this number and lets me do a scalar multiplication? Yeah, -1 plus 1. Clever rewriting of things. Because now what can I do on the left-hand side in this step that I wasn't able to do in the previous step? Distribute again. When I distribute, I get -1 times v plus v equals the 0 vector. I want to get rid of this v here that's on the left-hand side. What can I do? Yeah, you add its inverse, all right? Get rid of it. So I know the inverse exists, so I'll add the inverse to both sides. The right-hand side is going to simplify to what? Negative v, the inverse of v. I have to do 2 steps on the left-hand side. First, I need to, actually, technically, I need to do 3 steps on the left-hand side. First, I need to move the parentheses, then simplify v plus its additive inverse, which gives you the 0 vector, and then anything added to the 0 vector is itself. So I'm going to skip ahead to the end and get what the result is. But notice to go from here to here, there's actually 3 steps. I got to regroup, simplify to the 0 vector, and add the 0 vector. So there's 3 pieces in there that I didn't write. Okay, I know, lots of stuff, right? And lots of playing around with different properties. The whole reason why we went through it this way, though, is that we were proving it in general, right? I don't have to go back and reprove these now for every single vector space. That's why we're doing a theory of vector spaces, because if I can do it generally speaking, I don't have to redo it for every single new thing that I come across, right? I don't have to reinvent the wheel every single time. So that's why we're proving these properties, generally speaking, from the properties. Notice I wasn't writing in vectors in Rn here and proving it there. Okay? I wanted to prove it generally for whatever vectors we might be coming across, for whatever addition and scalar multiplication that we might run into. All right. Questions on how we did any of those proofs? Ready to do some things with the numbers? You're all looking at me like I said, this is the stuff that I love. So I'm an algebraist, so this stuff's fun for me. So, all right, we'll go play with some numbers. I'll make you happy, or at least make you less unhappy. All right. So I do need to do one definition before we play with some numbers here. We're going to focus on this type of structure that we're going to do, not structure, but this type of, I'll call it an operation, but it's not really that either. We're going to focus on this thing quite often in the next few sections. A linear combination of a set of vectors v1, v2, out to vn is just scalar times vector plus scalar times vector plus scalar times vector. All right. What we mean by linear combination of things is that we do number times object plus number times object plus number times object throughout the set of the objects. So that's what we mean by a linear combination. The linear idea, of course, comes from the fact that you're looking at, when we've talked about linear equations before, or linear functions generally speaking, that you're not doing weird powers of things or combining vectors in weird ways. We're just doing number times vector plus number times vector across. That's the linear part. All right. So a couple of problems they ask you to do, and I'm going to play around with R a little bit as well. Let's say they ask you, this is number 47 in your text. They say write the vector, they called it V in this case, 10, 1, 4 as a linear combination. And I'll typically abbreviate linear combinations so I don't have to write it over and over again. Of U1 equals 2, 3, 5, U2 equals 1, 2, 4, and U3 equals negative 2, 2, 3. Well, it also says if possible. It might be the case that it's not possible to write the one vector as a linear combination of the other three. That is one thing that we will focus on later on is, given a set of vectors, can we tell right off if it's even possible to do? All right, so let's think about how we would do this. The idea here is that I want a constant times U1 plus a constant times U2 plus a constant times U3 to give me that vector V, right? So let's just give them names. Let's say we want C1 times 2, 3, 5 plus C2 times 1, 2, 4 plus C3 times negative 2, 2, 3. We want that to equal 10, 1, 4. And we're done. That's what it means to write it as a linear combination. I want to know what those constants are. From this vector equation, can you set up a system of linear equations for me? Can you tell me what the first components, can you give me an equation that pops out of what the first component has to be? That has to be true about the first components. Say it again, Masana. I just didn't hear.
For the first,
yep.
By the first component, we'll do first of each.
Yep.
2C1 plus 1C2 plus, minus 2C3.
Good. If we equate the first components, right, I have 2C1 in the first one, a C2 in the second one, a minus 2C3 in the third one, and a 10 on the right-hand side. Tell me another equation from that comes up based on the second components. Plus how many C2s? 2. Good. Yeah, 2C3 equals 1. Yeah, exactly. That's from the second components. How about the third? Good. Yep, that's right. Good. Now we have a system of equations, all right? We know how to solve this, don't we? We would put it in an augmented matrix and row reduce is one way to solve it, isn't it? All right. Our augmented matrix here would look like 2, 1, negative 2, 10, 3, 2, 2, 1, 5, 4, 3, 4, right? Now, one thing I want you to notice before I go over and solve this thing, one thing I want you to notice is look at the first column. What does the first column here correspond to? Yeah, the U1, exactly. The second column is U2. The third column is U3. The last column is V. Yeah. So notice that I can put these right immediately. I didn't have to do this intermediate step. It's going to work this way every single time. I can just put these vectors in columns and make my matrix. Okay. So we can do this either on your calculator, but on R, I can define these vectors pretty quickly. So let's say I make my V was the vector 10, 1, 4. That was the V, right? I'm just calling it V. Okay. Remember to create a list or create a vector, I use that C command in R. So C all of those three things. I could also label these by number. I can say U1 is equal to C235. U2 is C of 124. U3 is C of negative 2, 2, 3. So I'm just entering the vectors in there individually here. Now, once I have these vectors in here, you can do different things with them. I'll illustrate that here in a second. But one thing that I want to form an augmented matrix with these three as my first three columns, and my V is my last column, right? So one of the things that we can do in R is use that C bind command. So it'll bind them as columns and make a matrix out of it. U1, U2, U3, and V. I can just do them as columns. Makes it a little bit easier to type that matrix in than having to type one big long list of all the numbers in there, right? And it also illustrates what's going on. And this is going to be something that we're going to come back to over and over and over and over again as we do these problems. One of our first steps in a lot of these problems is going to be make a matrix where we put in the vectors as columns. It's going to be one of the first steps. Do it in your calculator too, but on your calculator, every time you hit enter, it goes across the rows, right? It doesn't really illustrate the concept. The concept is to create your matrix with those columns. That's why I like this column line command here. It reinforces what we're doing. Okay. I do have to remember if I'm going to use the reduced row echelon form command, I have to load up that Pragma library, right? Okay. But now REF of A gives me those constants quickly, right? By the way, I'm going to expect you to use your calculator on an exam to do this. I'm not going to make you do these row reductions by hand, okay? I want you to use your calculator. Do not spend all the time doing your row reductions, okay? Because there's a lot of things that we're going to do. First step is going to be create a matrix and row reduce it, and then interpret what we get. I don't want you to spend 15 minutes row reducing a matrix. Okay? It's a waste of time. Okay? All right. So this tells me that we should have, see if I can write, switch. So we would have C1 is 1, C2 is 2, and C3 is negative 3. Right? So we should be able to check this on R as well. If I do C times U1 plus C, sorry, not C. If I do U1 plus 2 times U2 minus 3 times U3, what should I see? 10, 1, 4, right? That was the V vector. There we go. We do. So I can check the answer quickly. This is another advantage of doing this in a program like R over doing this on your calculator, so I can check my answer real fast. Right? More important than using R, say, does the concept make sense of what we did to find this linear combination? So if we wanted to do something that's a little bit bigger, we could still do it. So this is number 54. I'm going to write it on the board so I don't have to flip back and forth between. Flip back and forth between windows on my computer. So your vector V is 5, 8, 7, negative 2, 4. You've got 5 vectors that you want to write this as a linear combination of. 1, 1, negative 1, 2, 1. 2, 1, 2, negative 1, 1. Wow. U3 is 1, 2, 0, 1, 2. U4 is 0, 2, 0, 1, negative 4. And finally, U5 is 1, 1, 2, negative 1, 2. I guess they were pretty nice about not making big numbers in there. Again, the same directions as the previous problem. Find a linear combination of the u's that gives me the v. Same directions. What does your matrix look like that we would create? Let's start there. What would your first column look like?
Oh, wait, no. 1, 1.
There you go. Yep.
1, 2, 1.
Good. Yeah. So I'll take my U1 vector, make it the first column. The next vector will be 2, 1, 2, negative 1, 1, right? And it's down the list, correct? That makes sense for everybody? So 1, 2, 0, 1, 2, 0, 2, 0, 1, negative 4, 1, 1, 2, negative 1, 2. And then the final column here will be good. Fantastic. Good. So let me do this in here real quick. So there's my V. There's get my U1 in here. Unexpected. Oh, I forgot the C in front. It was unexpected that I got an error, is what it was. If I had a keypad, it would be even faster typing this in than on my calculator. 2, 1, 1, 2, negative 1, 2. And I already have my V in there, right? Okay. So again, I can make my matrix with that cbind command. U1, U2, U3, U4, U5, and V. That'll put it as columns. And then finally, last step is to reduce it. Yep. A lot of stuff going on behind the scenes, but when you're writing these things down for me on your homework or on an exam, I would want to see the initial setup, and then I want to see the reduced row echelon form. Okay? So our reduced row echelon form here, I do see the identity matrix on that left-hand side. And then that last column was negative 1, 1, 2, 1, 2, right? And so that gives us that we can check that negative U1 plus U2 plus 2U3 plus U4 plus 2U5 equals V. And again, the nice thing about having all of those things stored as variables in a program like R is I can check it quickly, right? I can do, I don't know if it'll do negative U1 or not. Okay, it's fine with that. Negative U1 plus U2 plus 2U3. Why am I looking behind me? I can see it on my screen. U3 plus U4 plus 2 times U5. And I should get that vector that we said, that V vector that we had. Again, this is why I wanted to introduce, this is this type of stuff now, why I wanted to introduce you into R. Okay? I know that some of you doing numerical, we're doing a little bit more work with it, which is also good. I just want to use it as a calculator where you can check yourself while you're doing your homework kind of things, right? Make it a little bit faster for you. You're going to need to be able to do this on your calculator as well, but it's going to be the smaller ones. I'm not going to make you type in a 5x6 matrix into your calculator on the thing. That's ridiculous. Okay? But if you have something like this on a homework problem, go to some other program and use the technology. Okay? And then use the after you use the technology to do the computations, then do the interpretation. That's what I'm interested in. Okay? Don't spend 20 minutes rubber reducing something by hand. Please do not spend 20 minutes rubber reducing something by hand. Okay? All right. Have a good weekend. We'll see you on Monday.